of planar graphs and their duals. So let's welcome Ellie.
Okay, thank you. I'm Ellie, and yeah, just as you said, I'm going to be talking about those planar graphs and their duals, looking at their spectra. So basically what my project is it's looking at graph theory. That's the bigger umbrella which I'm looking under. So graph theory, what that looks at is, as I said, graphs. But these graphs might not be your typical graph that you think of. They don't have the XY plane. They don't look at the length of the edges or anything. They just look at these, if you look at this example graph, which I'm going to go to. Oh, that looks good. Okay. Well, you can't really see it. But that graph up there is called a K4 graph, which you wouldn't know. But those points are called vertices, and the connections between them are called edges. So what that graph is looking at is what graph theory is looking at is those connections between those vertices. So what I looked at was spectral graph theory, and that is applying linear algebra to graph theory. So it turns out you can represent the graphs using matrices, and from there manipulate them, study them, find their eigenvalues. So there's also that matrix called an adjacency matrix, which you also wouldn't know because it doesn't say. But what an adjacency matrix is made of is ones and zeros. One represents a connection between two vertices, or adjacency, and zeros represent non-adjacency. So in this situation, you can see the zeros going down the diagonal, and what that would be is representing a vertex connected to itself. And since in our graph we have no loops where the vertices are connected to themselves, there's always going to be zeros in that diagonal unless there are loops. And then if you think about it, it makes sense that ones are in all other slots because it's a complete graph, so all vertices are connected to all others. Okay, so I'm going to attempt to explain eigenvalues here. So if you have your adjacency matrix, like that first 4x4 matrix, what you can do is you can multiply it by another matrix. And for example, this is just multiplied by that 1x4 matrix. And what you're going to get out for this situation is 2, -2, 2, -2. And then you can pull out, oh, you can't see the thing at all. Okay. So you can pull out the -2, and then you'll get back your -1, 1, -1, 1 matrix. And if you notice that 4x4 matrix in the end result is going to be the same as one of the matrices in the beginning. So if, or what that is called is your eigenvector. And so what you have here is your adjacency matrix, and if you multiply it by your eigenvector, you're going to get out that same eigenvector times a constant, and the constant is going to be your eigenvalue. And it says -2. You can't really see that though. Okay, this slide looks good. Okay, so it turns out that that adjacency matrix that we looked at in the previous slide was representative of this 4-vertex cycle graph. And so again, you can see the zeros in the diagonal and the other slots corresponding to the vertices connection. And so, oh, that looks good. Okay, so you can't read any of it, so just listen up. Okay, so for that cycle graph that we just looked at, we examined this adjacency matrix, and we saw that -2 was one of the eigenvalues. But there are also other eigenvalues, which you can see, which are 2, 0, and 0. So basically, the way that you find those eigenvalues is, if I'm going to state what we did in that example equation, it's AB equals lambda B, which is going to be the adjacency matrix times eigenvector equals lambda, or an eigenvalue, times that same eigenvector, what we just looked at. Yeah? Why? It looks so good. It looks like Chinese or something. So your mom. I'm going to wait. Thank you.
Sorry for the technical difficulties. We're going to start up again. We're able to see your slides here, but the online folks unfortunately will not. We apologize for that, and we'll see what we can do. But without further ado, Ellie's going to come back and this time present with her entire slides.
Perfect. Okay, hello and welcome again. I'm Ellie, and I'm going to be presenting on the perspective of planar graphs and their tools. Okay, once again. So what this presentation is looking at is the broader area of graph theory. And what graph theory is this examination of graphs, and these are atypical, not XY planar graphs. We're just looking at graphs like this one. Now read the complete graph, and the dots are the vertices, and they're connected by edges. And so graph theory is really looking at those connections between the different vertices. And so the complete graph, what that means just is that all vertices are connected to all other vertices in the graph. So what I looked at more specifically was spectral graph theory. And in spectral graph theory, you can use matrices to represent the graph. So you can use these linear algebra concepts. And then from those matrices, compare them and manipulate them and find eigenvalues and such. So in this situation, there's that matrix there represents that graph to your right. So the adjacency matrix has zeros and ones in it. Zeros are representative of no connection between two edges, and ones represent adjacency or connection. So as you can see going down that diagonal, there's all zeros. What that means simply is that there is no connection, and those dots are representing a vertex being connected to itself. So since there aren't any loops in this graph, then there's not going to be one in any of the diagonals. But the rest of that matrix does have one filled in. That's just because it's a complete graph. So all vertices are connected to each other, and that's why that is. Okay, let's explain eigenvalues again. So looking at that equation there, we have an adjacency matrix to the far right being multiplied by that 1/4 matrix. What you're going to get out of that is that 2, -2, 2, -2 matrix. And to find the eigenvalue, what we're going to do is factor out that -2 to end up with one of your original matrices that was in the first part of the equation. So what that -2 is your eigenvalue, and that 1/4 matrix is with the negative ones and ones in it is the eigenvector. So what this equation has is an adjacency matrix multiplied by that eigenvector, and what you get out of that is that same eigenvector multiplied by a constant eigenvalue. Okay, so what that matrix that we started with in that equation was representing was this 4-vertex cycle graph right here. And you can see again the zeros and diagonals and the other slots with the ones and zeros representative of this cycle graph. So that cycle graph, there isn't just that one eigenvalue of -2 we found. There's also 2, 0, and 0. And so to find these eigenvalues, we use that equation AB equals lambda V. What that is kind of both in our example, which was the adjacency matrix times an eigenvector is going to be equal to lambda, your eigenvalue, times V, the eigenvector again. So the way that we solve that is not just by trying matrices out, because that would take forever, but you plug it into this equation. The determinant of A minus lambda I is equal to 0. So you're just taking the determinant of a matrix. And what you're going to get out of that is a polynomial with lambdas. And the highest exponent of the lambda in that polynomial is going to be equal to the number of vertices in your graph. So what you do to solve for the eigenvalues is take the roots of that polynomial. And since you have, in this case, with the 4-vertex graph, a lambda to the 4th, you're going to get out 4 roots. So that's why in your eigenvalues there's 0 repeated 2 times, just because it had a multiplicity of 2 in the polynomial when the roots were taken. And also that's going to mean that even though there's 2 zeros, that's the same number for the eigenvalue, there will be 2 different eigenvectors for that number. Okay, so the applications of graph theory, it's still an actively explored field, but as you know, there's definitely applications in biochemistry and computer science. Looking specifically at spectral graph theory, there are applications in load sharing and equitable resource distribution. So what this is looking at a network. If you have these eigenvalues that you solve through spectral graph theory, you can figure out how to best distribute through the computers or whatever this network is, the workload in the most effective manner. That's basically what that is just representing networks through graphs. But also, just as a note, what I'm looking at is being graph theory is really just theoretical math. So what tends to be the case with this pure math is that you'll try to find these connections between different graphs and such, and then later on, after the theoretical aspects, applications can be found later. So what I'm doing is just looking at those connections between planar graphs and their duals, but we don't have applications yet. It's looking at the theory and pure math, and then continuing on later to find applications. Okay, so what I did for my research was I looked at those eigenvalues we talked about. I originally made 19 different graphs, and I just kind of drew them out, drew their adjacency matrices, and then found their eigenvalues. I didn't use the determinant equation because that would have taken a real long time. I just plugged it into this algebraic computing system called Mathematica, and so that gave me eigenvalues. And what I did is I found eigenvalues for the graph, drew the duals of the graph, and then did the same thing for their duals. So this is an example of a graph dual. It might be a little bit hard to visualize, but just what that is the dual of G, which G is going to be that blue graph, has a vertex corresponding to each face of G and an edge joining neighboring faces for each edge in G. That's just the general definition for that. So yeah, your blue graph is going to be your original graph, and the red graph is the dual. Basically, there's just for each face of this original graph, there's going to be a new vertex, and then all of those edges are going to be they're going to be new edges between the old faces. A little confusing, but that's basically what I did. So here's an example of some of the graphs that I looked at. What I did is look at those eigenvalues. So in that first one, we have a tree graph. So that's a pretty simple tree graph. I just looked at the eigenvalues for that, which were root 2, negative root 2, 0, and then compared them to the eigenvalues of the dual. So I was just trying to find correlations between them. So what I said is, or what I thought is, if you, well, they're not equal to each other, obviously, but if you take this and square these two, or these three terms, you get 2, 2, and 0, take the sum of that, you get 4. So the sum of the squares of these is going to be equivalent to the eigenvalue of the dual. And then what I did is I tested out on other cycle graphs, and they worked. And so here's an example of a cycle graph. So these numbers don't look quite as manipulatable or something, but I still tried to use that same, took the sum of the squares of these, so 2 squared plus negative 1.62 squared, etc. And that was equal to 10. But then if you go back to the eigenvalues of this dual, it's not just one nice number anymore, it turns into 2 numbers. So I said, okay, so how am I going to get 10 from this? Just take the absolute value of that and take the sum of that, so 5 and 5 is going to equal to 10. So that's kind of how I found that relationship between the graphs and their duals. I also tried it for other types of graphs. Here's an example. Turns out when you do this, you're going to get, or take the sum of the squares of that, you get 10. But then adding 4.53 plus 3.53, that's about 8. So that's not going to, the pattern doesn't hold for the other types of graphs. Okay, so from that, I made this theorem. The theorem is basically just what we observed in this tree and cycle graph. I'm just going to read it. Apologize, it's long. For cycle and tree graphs, if the original graph is called C and dual is notated C star, then the sum of the eigenvalues squared of the original graph is going to be equal to the sum of the absolute values of the eigenvalues of the dual. So what I had to do then is I created or stipulated that theorem, and I had to figure out how to prove it. So that's what a lot of my paper was on. I'm just going to kind of go through this proof. So first, what I had to prove is that the trace of A in each vertex will have 2 connections, because it's connected to 2 other vertices. So if you take this matrix and square it, you're going to get 2's in the diagonal of this one. So all that's saying is that the 2's in that diagonal are going to correspond to the degree or number of connections of the vertices in that cycle graph. So from there, I was able to show that the trace of A squared is going to be equal to 2 times the number of edges of the original graph. And that's because if you add up the degree of each vertex in your graph, then each edge will be counted twice because it's connected to 2 vertices. So add that up, you're going to get 2 times the number of edges. Okay, so basically what that proof was proving that the right side of that theorem I stipulated was equal to 2 times the number of edges of the original graph. So then I looked at the right side of the equation and showed that that is also equal to 2 times the number of edges of the original graph, that sum of the absolute values of the eigenvalues of the dual. So the way I did that was I looked at the tree graph and cycle graph individually. So in the tree graph, their duals are going to be pretty simple, just with one vertex with loops connected to it, and that's always going to be equal to 2 times the number of edges. And then same thing, just looking at that cycle graph, it's going to have a dual with 2 vertices with the same number of edges as there was in the original graph. If you take the eigenvalues of that, it's also going to be equal to 2 times the number of edges. So that's kind of how I proved that theorem, and I was basically just use these use specific examples and generalizations to show that. Okay, so once I had that, I also, during my data collection, had a lot of other graphs that I created and noticed things about. So in this further observations, I had this conjecture that I didn't have time to prove, but it's basically the same as the theorem, except it has, instead of an equal sign, it has a greater than or equal to. And the reason I have this is because I noticed in tree and cycle graphs, those are going to be equal to each other, but in other types of graphs, the right side of the equation is always going to be less. So in that situation, if you think about that example we had, the 10 is going to be greater than that 8 in that other graph we looked at. Also, I looked at the Laplace matrices, which are just a different way of representing those graphs, and came up with that and found that same theorem was true, except the right side was just multiplied by 3. And so those Laplace matrices are going to be, the way that you find that is you have the degree matrix of the graph minus the adjacency matrix of the graph. I'm not going to get it, it's just what the degree matrix is, but that's how I found out this theorem, but not a theorem. But if I have more time in the future to look at the graph theory or just from this paper, there are definitely things that are patterns that were observed, but I just didn't have time to look at them. So those are my references. And then for my acknowledgments, first and foremost, Oscar, thank you so much. You're so helpful in guiding me and teaching me everything. Also, Taylor was an undergraduate student. He basically taught me everything else about graph theory, so he was also super helpful. Lori, thank you for making everything possible, of course. And Sean, thank you for being my advisor. Cargill, Specialty Foods and Oils, they were really helpful in funding me for my research. And then Sophie and Topher, thank you so much for having me. And okay, thanks. Any questions? Yep.